Hello and welcome to this session, how to get started with SOLIDWORKS simulation. My name is Matías Robertson. I work for SOLIDWORKS. And let's have a look at our simulation tools product portfolio. We have three different packages for structural tests for parts and assembly: Simulation Standard, Simulation Professional, Simulation Premium. We have an area for simulation for injection molding called Plastics, where you can check mold defects, make sure you have a good plastic part for injection molding. We have flow simulation for liquids and gases, heating and cooling. And we also have SIMULIAworks products from our SIMULIA brand that is based on the Abaku's software. The SIMULIAworks is a standalone product. The rest is 100% integrated in SOLIDWORKS. And today we want to talk about how to get started. So I will focus on the stress area on parts and assembly that is included in Simulation Standard. Now, if you want to have a look a little bit what is included in Simulation Standard, I want to play you a short video to show what it contains. So basically it is structural tests, it is rigid body motion and lifetime checks with fatigue. But let's have a look at the video to show more details what we can do here and what we will cover. So SOLIDWORKS Simulation Standard is our entry package to simulation, to check stress levels, to understand where we have high stresses, low stresses, understand deformation, how stiff a product is, document factor of safety, and also understand contacts, see how parts and assemblies interact with each other. Fatigue, lifetime checks. We can also do rigid body motion, contacts, friction, and understand the forces being generated when we have parts moving. So if you're working with motors or cylinders, you can understand the forces or the power that is needed to accomplish your specification. You can also combine motion with animator to create realistic movements. And here we have a cable that is swinging back and forward. And also to explore results, understand the performance of your parts and assemblies. And all this is 100% integrated in the SOLIDWORKS user interface. So just use tools and you're ready to go. And the user interface is really easy to use. Quite clear what you're doing here. And we'll go through a little bit how it's working today. To get a fast result, you work directly on your solid models, and you get an instant understanding of how it's behaving here. So there's a lot of tools for a mechanical engineer to use to create better products. So we will cover in this session how to get started with all this. It is not that complicated, and I want to demyth about the simulation. So let's start about the theory behind this. What's the thought and what's the theory behind this? Well, we can get started with the stress-strain curve. If we take a metal bar and put forces on each side here and try to break it, we end up with a curve, a stress-strain curve. And this curve is linear in the beginning, and then it starts to deflect and deform. And what's happening here is that we are coming to a yield point, a yield strength. And then we have the ultimate tensile strength, and then we have the failure strength. And what we're dealing with here is the linear area, the linear stress, and this is what we call a linear static simulation. And this is what's included in SOLIDWORKS Simulation Standard. If we're passing the yield strength, then we need to move to a non-linear simulation, and that we can do with Simulation Premium. And we can also use SIMULIAworks products, and that really takes us all the way up to the breaking point, to failure, and have a really good description of the material behavior in the SIMULIAworks product. But we will focus on the Simulation Standard and talk about the linear stress. We often get the question, how accurate is really this SOLIDWORKS simulation tools? Well, I want to refer to a report that was published in a French organization called AFNOR. And this report shows that we have 1% of the ideal solution. This report, you can download it from our web page. and it contains 101 examples how to show the theory, how to show the solver, how accurate it is. So it is within 1% when it's set up correctly here, just to make sure it works okay. So let's consider something here when we talk about the linear stress and what we need to think about when we're working with simulation, because we need to keep the result under the yield strength, because then we are sure that the results are correct. And as you can see on the result bar, the yield strength in the material. So something to look out for is when we have a result, we can actually get a theoretical result that is above the yield strength, because we are working with the linear stress here. And if we have a result that is above the yield strength, you will see that in the result here on the material that we have passed the yield strength point. And this is a big red flag, because now we are pretty sure that the results are not correct. So pay attention here if you have passed the yield strength in any way in the result, because we cannot really trust the result since it's a linear curve that we're working on. So if you have passed this and want to have a result on this, you need to use the non-linear simulation using Simulation Premium or the SIMULIAworks products to get the correct result here. So pay attention for the yield strengths. We want to be under that. Okay, let's move on. So some rules we need to consider here for working in the linear area here. So materials are linear. We want to keep the results under yield strength, as I mentioned. Deformations are relatively small compared to the object. And geometry and loads are not changing during this step. It goes from 0 to 100% in one step. So if we can accept this, then we are okay to work with linear static simulation. So how to use it? What is needed to do a simulation? Well, we can do it in 4 steps. First, we need to set the material. We often use the SOLIDWORKS material. Then we put the load, and we need to restrain it, otherwise it will fly around here in the space. So that we put some restraints. This is what we call the boundary conditions. Then we mesh the part, make a mathematical representation of the geometry. And we'll talk about that more in a moment. And then we run it and get the results directly on the model using the mesh. And these are the 4 steps we need. So this is how it looks, very, very simple. So we have the material already, SOLIDWORKS material. We put down the force. I want to have it in the front here. And I use the geometry a lot to put my boundary conditions, choose directions if I want to. So now I put the force and I want to restrain it here, if it's going to be fixed or a hinge. And then we can measure it real quickly here, and then we can run it. And these are the 4 steps that is needed to run a simulation. It is quite simple to do, and then we can look at the results. But we will go through all this in more details now, all the steps, and see a little bit more what we can do to get a result. So let's start to talk about a mesh. What is a mesh? Well, I said that there was a mathematical representation of the model, and that is something we need to do to capture the geometry in a good way, and from that we get the result. So the technique is to capture the geometry in a good way, and the way that the mesh is built up is it looks like small triangles here on the graphics, and these triangles are what we call the elements. They are 3D dimensional in this case, and these elements are built up with nodes. These are the endpoints, and the nodes are connecting to other elements. And there are different kinds of elements we can use depending on what type of geometry we're using. So we want to capture the geometry in a good way to have a lot of elements describing the geometry. And we have 3 different types. We have beam elements for good for use for weldments, for welded parts, for welded beams. We have shell elements used for thin parts, good for sheet metal and surfaces. So if you have a sheet metal part, it will automatically recommend and set the setting to use the shell element. And then we have the solid element, that is a tetra element that fills out the 3D geometry and capture the geometry with these kind of elements. These elements could combine with each other. You can use them together in an assembly, and you can also change them if you want to. If you want to have a beam element, you can change that into solid element, for instance. So we also have some settings on these elements types. I mean, it's all about filling out the mesh and make a setup that is balanced about calculation time and accuracy. And this is kind of the balance we do with simulation to find a good result by using the appropriate amount of mesh elements. And I said we have some settings to highlight here. We have a default setting that is using a high quality elements, and then we have a draft quality elements we can use that has less nodes. There are also some mathematical differences here. The high quality element has a quadratic variation, and that could capture the geometry in a better way. The draft quality element has a linear variation. You can see it doesn't really capture the curve here in the hole in a good way. But the benefit with the draft quality element is that it is fast. So this is something maybe you can use as a quick run through to see that you're getting the result that you're expecting. But the default setting is the high quality element that have more nodes and a quadratic variation. We also have some differences about the stiffness between these two. The draft quality element is a bit stiffer than a quadratic element. So use draft quality element to get some speed. That's the benefit of using it. Otherwise, use the high quality element for all cases. Okay, so when we are creating a mesh, we want to capture the geometry in a good way, and this we can use some automatic tools and some manual tools, and we'll see how we can apply those in a moment here. So we want to capture the geometry, the mesh and the elements in a good way. So let's have a look at how we can mesh a part and what tools we are using here. So we are creating a study. We are jumping directly to the mesh settings. And we can use a finer and a more coarse mesh, and it is a size. We can type in the size directly if we want to. And it looks at the geometry to suggest a size. We also have 3 different algorithms for the mesh creation. So let's use the standard one here. That creates quite uniform mesh everywhere. And depending on the tolerance, it can also refine it a little bit. So let's zoom in here on this area. The small fillet here is not so good capture here. So we want to make a finer mesh here. And there are different techniques we can use. We can use a setting, a general setting that automatically looks for small geometry here. And that will automatically refine the mesh here over that. And that's something we can use. If I manually want to refine a mesh, I can just select my interest here. I want to have a finer mesh on this surface. And then I could type in a finer value here. And then if we remesh it, we will see that we have a finer mesh also here. So we could combine local settings with some general settings here to capture the geometry and create a mesh with appropriate amount of elements. So let's talk a little bit about loads and restraints and how we can set up and work with the model on that. So we have quite a few restraints and loads we can use. Force, torque, pressure, gravity, centrifugal, bearing loads, and displacement. We can also import from flow simulation some flow effects on pressure, and also use remote loads and mass. So let's see how we can work with this in the part. So if I want to create a load, a force here, I use my geometry here, and it is quite clear. Look at the arrow, where they are being placed, and also what direction they are. So I want to type in my value here, and look at the direction of the arrows. So I'm selecting and using the graphics as my references here to see what's direction, if it's going in or out. So let's push it down. Now we need to make some restraints here so it doesn't float around in space. So I'm using a fixed geometry here. And there's a preview here to show a little bit of how this restraint is operating here. If it's gliding on the surface, like this one, or if it's a hinge that is more rotating. These are the most common ones to use. And we have some more advanced ones to use symmetry and references in different directions. But let's use a fixed one that is not moving at all at the bottom here. And yeah, that's basically it. Now we have material we already set. We have the boundary conditions. We have the mesh, so it's ready to run and get the result. And the result could be a bit shocking here. It looks a bit exaggerated, but it is over exaggerating the deformation a lot. So we don't have that big stress here. So it's exaggerating a lot here, the deformation scale. And this is something you can change. And also check the yield strength here, that we are below the yield strength point here. So I just want to make some animation here, and the default is 5 frames. I always change that up to at least 20 to get a more smoother animation of the deformation here. So this is a lot exaggerated, but it gives us a good idea of how the parts and assemblies are behaving during deformation, how it is deforming during the load here. So if you want to change the scale here, this is done under edit definition, and here we can use any scale we want, or manually type in a scale that we might find more appropriate. So deformations are quite small, as I said, but it's always good to exaggerate them a little bit more to give a good understanding of how the parts and assemblies are deforming under the load. And here we see the animation and how the loads is building up there. The stress is building up here around this fillet. Okay, so this was a little bit of how to set up some loads and restraints. So let's talk about contacts. When we have assemblies, how they interact and how we can use contacts to get a more realistic result. So here I have a plate and a shaft going through a hole here. I have set 2 different materials using multi-bodies or an assembly here. And I want to use contacts between those parts. By default, all touching faces are called bounded. That means that they are connected. So I'm going to put some force to get a contact between those parts. So let's put the force at the end and also fix it on the backside and underneath here. And then we mesh and run it in one go here, just to see the default setting here and what we can get from this. And if you see the result here, if we zoom in what's happening here in the contact, it is acting like a super glue. Let's add up some more animation, get a smoother animation here. You can see on the top side here that it is in contact on both sides, on the top side and on the bottom side here. So this could be correct if we have like a super glue inside here. But if I really want to check the contact, I need to separate those faces into a correct contact behavior. And by default, everything that is touching is bounded. So let's create a contact set. I want to specify what surfaces are in contact, and we have some different contacts that is bounded. There could be allow penetration. We can use shrink fit, but I wanted to use no penetration. That means that they are touching, and they can also separate if needed here. And then I need to select exactly what surfaces are being in contact with each other here. So use select other and make those surfaces. Now, a simpler way than selecting what I did here is just to look for touching faces. Just select the components, and then it will automatically recognize the touching faces. So this is a much faster way to identify a contact and say that this is a no penetration contact. So we can have the general setting that is bounded, but locally we have now defined a contact between those faces. And that's it. Now we are ready to go here. So let's run this. The reason why it is bounded by default is contact takes longer time. Everything could be in contact, but we need to specify this and get a good performance in the part. So now we can see here that all the energy is being here on the bottom side here. We have all the stresses going down here on the contact force here. And let's take a section. Let's view the section here. And here we can really see on the top side here how it's behaving more correctly here, that we have a contact between those parts on the bottom side. And it is really separating here on the top side. Also, the graphics is exaggerating about 40 times, but it gives us a good idea to visualize the contact on the bottom part, and it's being separated on the top side here. So use contacts to get a more realistic result on how parts are interacting with each other, and using this contact setting to get a realistic result here. Okay, let's talk about connections. We also have some other tools to connect parts and assemblies with each other. So we have connections for springs, pins, bolts, bearings, and welds. And if you have toolbox parts, you can those will automatically be transferred into bolt connections. So with bolt connections, we can check that the bolts are correctly sized so that they are not overloaded, and we can get some special reports. And here we have some checks there that shows that there are some bolts that are overloaded in this case. Right, let's have a look a little bit more what we can use with the results. We have seen some results already, but I want to show you some other good tools that I think it's important to use. One of my favorite plots is called an ISO section here. And here we can go through and see the high stress area in the part and go through that as a slider. And we can also see it from the other direction, go from the low stress areas up to the high stress areas. So this is a really good tool to isolate and view the high stress areas in the part. And you can create as many plots as you like and use different settings for each plot. So use a section, the ISO view, and so on. And here we also see the deformation. You can change the scale, units, anything you like here to get a good plot of your results. Use it for documentation. So if you want to have some more accuracy here, more numbers in the units. And also factor of safety. Looking at the material, what is the factor of safety of your design here? And use it for a plot, use it for documentation, and you have a good result here. Now you can also extract information where you find it interested. So if I want to extract and see the contact force here, or the stress areas. Let's hide this shaft. Just use hide components, and those will also be hidden in the plot result here. So I can use a probe setting to extract information on certain points where I find it interested to get values from that, and use a plot. So you can see a curve being shaped here. Or if you want to use an edge or any geometry, you can get a lot of points more automatically to get a nice curve of the forces or stresses in this area. Use it for documentation and so on. So there's quite a lot of information to extract the result. Another good plot I want to show is called a design insight plot. So you remember this ICView setting here. So if I want to remove some areas, looking at some low stress result here, I want to use this as a guideline to remove material, because this is very, very little stress here. And I can use a plot called design insight plot that keeps a display state of the low stress areas in a part here. So I want to keep this plot, and now I can see some results kind of transparent of my part here, and I can use this as a guideline to remove material. So manually I take a decision here that I want to reduce this transparent part here, because we have so little stress here. It's not really using the material here in a good way. So I'm manually cutting away this low stress area from the part. So use the result as a guideline, and then just rerun the model and could continue to work with it. So all the plots are being saved here when you continue to work. So use a lot of design iteration, use a lot of tests to verify and optimize your part. And this is how we can do it manually. We have other tools in other packages like topology optimization that make this automatically, but this is the manual way. So I hope you have found this interesting so far, and I would like to invite you to a Simulation Get Started kit. This is a kit that contains a 3-month term simulation standard license. This license is standalone, it's not a floating license. And you get 5 Get Started videos about theory, mesh, contacts, connections, results, and rigid body motion. And these videos are more extended. These are about 30 minutes long each. And you can get all this package from your local reseller. So contact your local reseller for more price information. I think you will be surprised how little investment there is in this. So just a recap, we have looked at how to get started with SOLIDWORKS simulation, looking at the SOLIDWORKS simulation standard with the stress on parts and assembly, and deformation and factor of safety and so on. So this package, Simulation Standard, is a good package to get started. And I just want to summarize what we have seen so far. So it is a good tool. It is an easy to use tool for engineers. It is 100% integrated in SOLIDWORKS. Use it to reduce errors, reduce cost, increase performance of your parts, increase the quality, and overall it helps you make better products. So thank you for joining. Bye bye.